Hi, good afternoon, everyone. My name is xianhang, and today I will introduce the chapter 14, comparing the state machines. As previous lectures, we talk about the linear temporary logic formulas, and we started at the linear temporary logic formulas, and which will give us the idea of the comparing state machines. First of all, the linear temporal logic formula will give us a sense of the behaviors of state machines. When you make a statement like a state machine that a particular linear temporal logic formula holds for a state machine, which thing is the traces of the state machine that for all traces that the state machine can execute, that temporal logic formula will hold. Your temporal logic formula may include constraints for some inputs. So you may be asserting the state machine behave in a certain way, given the inputs include the assertion of the outputs. You can also include the assertion of the states that the state machine goes through, and so on. So if you give a particular temporal logic formula, there will be many possible state machines for which that temporal logic formula will hold. In the context of the state machine, some state machine will alter into deterministic. So what that means, given complete the sequence of input, while the state trajectory of the machine and the output of the state machine are fully defined. And in another case of non-deterministic state machine, given the sequence of the inputs, you may get multiple behaviors from that state machine. Non-deterministic state machines actually play a role like alternative way of specifying behaviors of systems. So, in a sense that a linear temporal logic formula is equivalent to a family of state machine. So, in some cases, you assert temporal logic formula holds for particular state machine. You are establishing a relationship between that state machine for that temporal logical formula will hold and the family of the state machines. The key thing here is when you see a linear temporal formula hold for a state machine, what you're really doing is to compare state machines. So today we will zoom in the idea of comparing the state machines. And we will define what it means for two state machines to be equivalent. And we're also going to define for one state machine to refine another. So this is our goals today. And why do we need this? The notion of refinement is very important. The idea is that suppose you have a design of a system, maybe a particular implementation, and now you want to substitute or replace your design with another design which has more details, or maybe a new design within many novel technology. So how do you know this design of the new ones will behave the same way as the old design? So to prove concretely, can we replace one component in the system by another and be assured that it will continue work correctly in this case? So if we want to replace the Cortex A9 core by a Cortex A12, will them behave in the same way? And what is the meaning of behaving in the same way? Different perspectives will give us different answers. In an engineering perspective, the answer will always be no, because it cannot behave the same way in this perspective. For systems, the notion of equivalence does not exist, and does not make any sense. But for the models, it actually does. Think about that. A piece of software and a model of behaviors, and the C program actually specify a whole family of possible physical events. Um, so there are many implementations that will give you same executions. The same executions of the C program within the semantics of C. The C program is a model, and in fact, we will work entirely within the context of comparing models in this case. And the issue is that we want to compare the models less detailed and with more details model. So the same questions. What is the meaning for two-state machine to be equivalent? Let's see an example first. Um, Assume you have a controller for an iRobot. Look like picture below. Here is a state machine that have two states. You can see upper left in your screen. It has two states. One is tilted and straight. And also suppose we have some sensors that can take in accelerometer data and telling us whether the accelerometer level or not. If it's non-level, we want to change into tilted state and rotate the robot. And if moving straight, it becomes not level anymore. So then we want to take a transition into the tilted state and rotate again. So we want to rotate until let it tell us the accelerometer is level. Uh, this is the central algorithm that you might use to point the robot straight by balancing the two accelerometers 45 degree angles. Um, so there is a description of the behavior. It's an abstraction and it's a model. Actually, physical robot does not act like this. It's more complex. This abstraction is very simple and easy. Okay, and right now, suppose there is another state machine and in the below position, and what it says that it only have one single state, and it have a driving state. The sensor tell us its level, and then it will self loop to produce the output into forward. And if it is not level, it will rotate. So are these two state machines equivalent? Specifically, the M1 is equivalent to M2. Um, well, and in what sense? That means in what kind of perspective you look at into these problems. And some of you may assume that they have different number of the states. Uh, yeah, the M1 got two states, but the M2 only got one state. So they are not equivalent. But some of you, or maybe you will see that they are equivalent because from the abstraction or the description of the state machine, you can see that the input and the outputs of M1 and M2 are the same, right? So if we focus on this sense, This is one type of equivalence named language equivalence. That means their input sequence and output sequence are the same. So you may be thinking they are equivalent. Equivalent. That's right. These two-state machines and also happen to be deterministic. Consequently, so they are in the language equivalence level, they are the same. They are equivalent, and consequently, their equivalence is rather in a strong way, which means the above model is stupid, right? Why? Because they are equivalent, so that means we only need one state so we can handle these situations. But the M1 got two states to handle all possible situations. So the M1 maybe look like more stupid. Um, then we can move into the another interesting notion of equivalence. It is really has to do with the inputs and output. So the abstraction of the machines, two-state machine may have different number of output and different data type of inputs. In this case, the number of the output and the type of the data are the same, right? The output is forward and the rotate is the same, and the input is pure, which means the absent and the present. The input data type is the same. So this is another notion of equivalence, which named type equivalence. Type equivalent does tell you the ability to substitute one state machine to another, which means if one machine put into context into system, communicate with another machine, communicate the same data type, and then substitute machine will also communicate within the proper data type. It's also helpful for your refinement. For example, if one state machine have a bug, when you fix the bug, you probably want the replacement machine to have the type equivalent. So the second is the language equivalence, and as I mentioned before. So notice that for every input sequence, the two machines produce the same output sequence. So that's the notion of the language equivalence. The third one is simulation, and in this case is bi-simulation. This one is very subtle. This one focuses on the states, but does not require the structure of the states to be identical. What it does is, for each state in one of the machines, there is a state in another machine such that henceforth the behavior can be matched. To be more precisely, reactions the input transition to the similar state. If you get the input, you will react the same way and transit to a state that is in a similar correspondence. This is a very subtle concept, and notice that for every state of M1, there is a corresponding state of M2 that will react the inputs in exactly the same way, and then transition to another similar corresponding state. So therefore, the M2 is simulate to M1. And also, it's a stronger form of equivalence than the language equivalence. Because for deterministic machines, language equivalence and bisimilarity are the same, but for the non-deterministic machines, they are not. And we will go to further into this notion. But first, and then we will go into the refinement, and it's very interesting because the refinement is a weaker conception than equivalence because it does not require symmetry. It two-state machines M1 and M2 are not equivalent. May nonsense be related to M1 may be type comparable with M1 that it can replace M1 without causing a type conflict. And the second is M2 may be a specific specialization of M1 in that it can produce only output sequence that M1 can produce given the same input sequence. And this is named language containment. And M2 may be a specialization of M1 in that every reaction M2 can produce only output values that M1 can produce. So this means M1 simulates M2. It's simulate. So there are also third refinements of the third types of refinements compared with the equivalence, and we will go into details in each type of refinement. And at last, when we talk about the simulation, we will go into further detail with the bisimulation. So first, let's go into the type refinement. First, it still substitute one and another. You see that, for example, you can see in the object-oriented language routinely. As a fact, any place you use an instance of a class, you can also use an instance of a subclass. Class and the subclass, like in Java, does not have type identically, but they have substitute ability. Let's look at an example before we go into the language equivalence. In this case, the state machines, the type signature of its input and output. In particular, we talk about a state machine that have input X in the upper left of your screen. That have an input X and with the data type of the V sub X. So the V and also the V sub X is a set. So if the X is a pure the size and if the V sub X will be 1. So let us focus on the X. If we want to M2 to replace, we want M2 to replace the M1, but it has different input type. One is the V sub X and one is the V sub X prime. What is the constraint of the data type we need for this replacement? In another word, if we want to replace the M1 with the M2, but they have different data type, so that means they are not type equivalent. But we still can replace the M1 with within the M2, but there may exist some constraints of the data type. So what is the constraints of the V sub x prime with between the V sub x? And we have two conditions. First one is that we may need the V sub x may be a subset of the V sub x prime. And second is that we maybe need the V sub x prime to be a subset of the V sub x, which is true. So the idea is that because we know the M1 works fine with all V sub x, so if the V sub x prime, this one, the V sub x prime is bigger, is harmonious, right? It contains all the possibilities in V sub x. So it's harmonious. It just means that our substitution machine M2 can handle more inputs than the original machine. If the V sub x prime is smaller, that means there are some inputs of the original machines in M1 that M2 cannot handle. And then let's focus on the output. There are also two same constraints. One is that V sub y is a subset of the V sub y prime, and the second is that the V sub y prime is a subset of the V sub y, which is true for the constraint if we want the M2 to replace the M1. Well, right, now we need our original output to be bigger, right? Because if our substitution machine M2 output is bigger, then our original machine cannot know the new output into the environment. Notice that here is the opposite relation here. The inputs can use big data type in the substitutions. The outputs must use a smaller data type. And also you may find that the M1 have two input ports, but the M2 only got one input port. And also the M1 just got one output port, and the M2 got two. The different number of ports, but it's harmonious because we can ignore the input and the extra output that M2 will produce. So the refinement can have more outputs and less input. That is the reverse of the data type. The data type requires bigger inputs data type for refinement machine and fewer outputs data type. In short, the type refinement can have more data types but fewer input ports and more output ports but fewer output data types. So now let's take a look at the language containment. But first of all, let's recall an example that is garage counter. Um, counter. You can see that the count start at the zero, then given an input up and another input opposite down as present. We transist 1 to 0. So we get the data types in addition a behavior. We give this state machine. This is states and this is a behavior. So suppose we have with 99 spaces garage counter M1, and we have another garage counter M2 which has 90 spaces. And can we replace the M1 with M2? And why M2 is a type refinement of M1? Well, because the output produced by M2 is 90 spaces, and it won't be expected by the environment if M1 work, because M1 got 99 outputs, 99 spaces. However, if we reverse the condition, that means if we want to replace M2 within the M1, it does not work fine, because if the output of the M1 is too large, in this case 99 maybe work fine, but is like 1000 or 2000, maybe the M2 cannot establish all of this output that M1 produce, so the reverse cannot work very fine. And next, actually, this machine is exactly equivalent using the in the below you can see that we using the variable instead of enumerating the numbers, and it's just a different synthetic equation for the machine. Language equivalent, and both machines are the deterministic, and it's also similar. And again, in this example, the M1 and M2 are again equivalent. So how to define the equivalence? Is equivalence always required? So for deterministic machines, the language refinement is required. For non-deterministic machines, we need simulation. So when we talk about we want to talk about the simulation, which is strongest equivalence, which is bisimilar. We need to go into details of the execution trees of a state machine. The execution trace is a sequence of the form, and while all the sequence is treeable, here is the input and the state and the resulting the output. For start I0, our input is x0, and we will get the output y0, and then it will transist into S1. For language refinement, the traces will comprise only of the inputs and the outputs, not the states. You only care about the x0 and y0 instead of the S1. So the language L of the state machine is a set of all of the behaviors. So all possible sequences of the input, what is corresponding output. So the language refinement is a subset of the behaviors. So if I have a certain machine M1 and a machine M2 have different languages, but if every member language of M2 is the member of the language M1, then the M2 is the language refinement of M1. M2, which also means M1, M2 can replace M1 if its observable behavior is a subset of the M1. But, so if we have a non-deterministic machine, the researchers said that the language equivalence is not enough in general. Here is an example. Even though their language equivalent is the same, which have the same input and the same output sequence, here we have the state machine M1 with the pure input X, which means it's either present or absent. This particular machine with X absent will transist to state B, and it will produce the output 0. Subsequently, when X is present, it will produce the output 1 or the output 0 non-deterministically. So if we look at the behaviors for this, let's assume the input always be the present. The possible sequence will be 0 follow 0, 0, 0 follow 0, or 0 followed by 1. About the M2, when X first present as the input will produce 0 as the output. But in the subsequent reaction, when X is present, what it will produce depends on which these two stages and up to language of this machine will be the same, right? For language perspective, these two machines are identical. Why do we say that they may be observably different? We can see that the M2 machine flips coins earlier, right? Earlier than this M1. So it make a commitment earlier in time. M2 make a commitment earlier in time about some non-deterministic choice. Instead, the M1 will postponed the commitment, which is saying that I'm not decided which way to go, so I postponed the decision, um, and which will also make the environment sneaky. That I'm two will make the decision earlier than I'm1. Um, so does M1 will can replace the M2? Suppose M1 is a specification, so everything is working is fine. It also is fine to replace it with M2 because at each step, any move M2 can make is okay. Because any move M1 can make it is okay. Because, however, if M2 is if we reverse this assumption, we want M2 to replace the M1. However, the M2 is a specification. Then, after the first execution, there is no longer any choices to be made. That means it cannot fit into the M1 situation. So it is not okay to replace it with M1 because in the state B, M1 is always capable to making a move that M2 cannot make, right? This is not validated substitution because after the first execution, it cannot behave in a non-deterministic way. Okay, and so now let's take a look about the simulation relation. Um, First relation is simulation relation, and the second is bi-simulation. In this case, you can see that I'm1 simulates I'm2, and I'm2 simulates I'm1. But notice that they may be not bi-simulate relation. But if M1 is bi-simulate with M2, then M2 is also bi-simulate with M1. This is very subtle descriptions. But first of all, let's just determine whether they are in a simulation relation. So first of all, let's start the matching game. Each machine um, starts at the initial state, and you put the pair of the states into the simulation site. If the following case occurs, we check if M1 simulate M2. The ordering of the pairs matters, which means the EA and AE is totally different because when you check the M1 if is simulating with M2, we must let M2 move first. So the motivation is that if M1 simulates M2, then the M1 should follow the M2's movements. The M1 should try to mimic the M2's movements, right? So we must let the M2 move first. So to check that M1 if it can follow the movement. Let's see. What means that it can, in this case, uh, it certainly can. What when x is present and the only output is 0, right? The only output is 0, and M1 given present will produce the output 0, so it matches the moves. If the input is absent, it will still match. So we put EA into the simulation state. For the next move, we need to consider two possibilities. The first possibility is the upper transmission move to F. Can M1 still match with M2? The answer is yes again, because M1 can choose the output to be same as M2. Notice that we choose the output, which means that our question is that can M1 will simulate with M2? Not it will simulate. It can. It can choose to execute to 1. And also we can see the second possibility. It does matching. Then we have to consider the final states that only the only thing M2 can do is state, and M1 can do is starter. And so we put all the possible simulation pairs, possible behaviors into the simulation set, and because we cover all of the behaviors, so we have a simulation relation. That means the M2 can replace M1. And also it's easy to understand. You keep more flexibility when you postpone the choices. So suppose we construct the reverse relation. So whether M2 simulate with M1, and now we need to move M1 first, right? So we put AE first, and we check if they are matching. The first pair will work fine. And now let's see the second move. The M1 move to the F. As M2 move to the M2 move the M1 move to B, and the M1 move to B, and M2 have two possibilities. Let's assume that it will move to F. Can M2 still simulate the M1's move? No, it cannot. Because M1 may go into the to D, right? In this case, the M1 may go into the D, so the output is 0. But the M1 only got one possibility to go is G. And the M2 cannot produce output 0 at state F. So M2 lost the matching game, right? So this kind of matching games will give us the idea of which state machine will whether will simulate to another one. Um, if if one state machine does not follow the movement of another state machines, that means it does not simulate to another one. And here we can conclude some conclusions of this simulation relation. First of all, the postponing decisions is more powerful than not, which means you will get more flexibility to deal with the decisions. And also the second is free will be more powerful than the pre-ordination. It's also same with M1. And so M1 can do anything M2 can do, but M2 cannot do that M1 can something M1 can do. So M1 simulate to M2, but not in the vice versa. Mm, here is a formal definition of the simulation. Um, I won't give it go into the detail, but you can read of them these terms and formulations, because I believe the formal example is very clear that doing the matching game, uh, first we determine who move first, then let we check another machine if it follows the movements to make the matchment. If they are matched until we cover all the behaviors, then one state machine is similar to another. So at last, we will go into the key idea of the bi-simulation. It's a stronger equivalence than the language equivalence. The M1 is similar to M2 if they are type equivalent, and when playing the game, on each move, either machine can move first and the other machine can match its move. This is very subtitle. Please focus on this on each move. On each move is different from the simulation relation, because we determine the order of movements in the simulation relation at first, but in the bi-simulation, on each move, which means at each movement we can the reorder who go first. Then we check if it still got the same movements. So it's a stronger form of equivalence. So the key thing previous M2 cannot simulate M1 because the first state it has made a choice. But in this machine, you can see here, it can always choose to go into J, so that it will match. You can see it will match the M1's movements, but then we reverse the order then we reverse the order. M1 move first, so that the M2 cannot match that. So switch the order who go first is very important. So M1 simulates M2, but they are not bi-similar. This is a very good example, but maybe the very simple example. They are not bi-similar, but they are simulate together. Because if you go to F, then you can if you go to F, then we reversed, and here M1 at the B, and here we reverse the order. Um, we let the M1 move first, so it will have two choices. It will go to 1 or go to 0. But at F, we only got one possibility, so that they are not bisimilar. But they are similar because we can let the M2 just go to the G, so that they will be similar. So it's possible to have two machines that simulate each other that are not bisimilar. Um, Here is bisimulation and the formally defined nations. Um, but also, if you look like this example, you will get a better idea of the biosimulation. It's different from the simulation because you can reward the checklist at each movement. That will make it harder, make the matching game very hard. Um, and also, here is a simulation and the trace contentment serial. If M1 simulate M2, then the language of M2 is the subset, which also means less or equal to language M1. If language, but the reverse is not meaningful. If language M2 is equal or less than the language M1, it not necessarily needs the M1 simulates M2. So at last, I want to see that in the real life, the state machine is very complex. Usually, it contains thousands of states. So it's hard to determine that there are two machines equivalent because it's hard to tell if the type equivalent or language equivalent because it has thousands of input, thousands of details, and thousands of data type. But bisimulation is a very easy algorithmical check, and you can do by exhaustive search. Just start initial state and just pairing the next state and check if it matched until you find a situation that one machine does not follow or reach all the possible behaviors you can end. And it's a very easy way to check if two state machines are bisimilar, but it's hard to tell in real life its type refine a type equal or equivalent or language equivalent. And at last, I want to go through again the biosimulation and simulation definition again, because it's very substantial and confused. Um, uh, you can see from the biosimulation definition uh, here that there are only one difference between biosimulation formally definition between the simulation ones. They just you can see at the second step, the biosimulation only extend to it look like a reverse or look like the reverse the orders or look like the um, to check each of the each steps of the another machines if will match with another in the by by orientation. So the orders of each step is very important. But in the simulation, we only check uh, in one orientation. So we made the order at first because we want to check M1 is similar to M2, so that we let the uh, M1 move first to check if M1, M2 will follow the movement. So here is the summary of today's lecture. If we want to check M1 if it's a type refinement of M1, so we can the M2 can replace M1 without causing type conflict. As you can remember the example of the data type, we can have more data type of input but less output data types. And also the second is if we want to check M2 is a language refinement of M1, the only thing we need to do is to check if M2 can produce only output sequence that M1 can produce, given the same sequence. And third is that if we want to check M2 is a simulation refinement of M1, we just need to check at every reaction if M2 can produce only the outputs that M1 can produce. Remember our matching game. We let the M1 move first, then we check M2 if it can follow the movements of M1. And at last, we introduce a very subtle idea of biosimilar, and it's the strongest equivalence, and also it's a simplest, and also more realistic in our real life because you can check it using algorithms. At each state, either machine can produce only outputs that another can produce. So it's by orientations. So in our case, if M1 is validated in a system, then so is M2. While only the meaning of validate varies, alternative terminology. M2 implements M1. Here, M1 is taken as specification. So thank you all. Here is today's lectures. Thank you very much.